Hello, so in this video, we are going to learn an extended version of estimation problem. In the previous video, we learned a point estimator. That means we are curious about a parameter of interest. So we are going to calculate something from the data and use that as an estimator. And the conclusion was that when you're curious about the true mean, you can calculate the sample mean, and that is the best estimator in terms of unbiasedness and efficiency. And if you're curious about the variance, then you can use the sample variance formula rather than the population variance formula because the sample variance formula is unbiased, right? So today, like now, I'm going to think about a different example. So to extend the framework. So like many years ago, when my son was born, like when my wife was pregnant, the due date was February 15th, many years ago. So this is another estimation problem when the baby will be born, right? So then additional questions like actually the reason why we are doing this estimation problem is during the pregnancy, like the expecting date. The reason why we are doing that is because we need to make some decisions based on the estimation results. Like until when can she work, right? That's the first question. We wanted to know when the baby will be born, and may I schedule an appointment on February 10th or not? So like there was a conference. Really, there was a conference in like late January. So I was curious if it's okay or not. So anyhow, we would like to answer those questions for scheduling problems. We would like to estimate the due date, the expecting date. The problem is, even though the due date was February 15th, it doesn't imply it is the baby will not be born like on February 14th or earlier, right? So we know that the due date is just an estimate. It's likely to be wrong, like very likely to be wrong, and so it does not guarantee if it is okay she can work the day before the due date, right? You need to have like a more like buffer because we know there will be error, like estimation error will happen. Okay, so then a solution to that problem is like this. A more informative estimator, a form of estimator will be like this. The baby will be born between February 5th and February 25th. So interval may help better. So like if the doctor just told me, just do not make any schedule between these two dates because it's most likely when the baby will be born. Okay, that's more informative, so I can schedule accordingly, right? So we are going to use this idea in our estimation problem. We are going to think about interval estimation rather than a point estimation. What we have done earlier was the point estimation because we are estimating a parameter by a single number. What is the mean? Then you just give a number as an answer. And it is good, it is not bad because it is simple, very intuitive way, clear what you are talking about. So it is nice, but the problem is it's not accurate. And not only it's wrong, but also it does not tell how accurate your estimation is. In like a one point is almost always wrong, but like it does not show any additional information to compensate that. Interval estimation is better in terms of that dimension because we are giving instead of a number, we are giving an interval where the truth will be included, right? It provides additional information than a point estimator because it tells you how accurate you are. For example, if you are sure about your estimator, then you don't need to allow large margin of error. Like your estimator will be small because it is certain that your result will be there, right? However, if you are uncertain, you have to increase the length of the interval so that you to reflect the uncertainty, right? Because you don't know where it is, so you can just use a wide interval because you are uncertain, right? So like let's formulate that idea to like statistics, right? Suppose that we are estimating theta, we are interested in theta, and assume that we already have a point estimator theta hat. Like I said, like for mean and for the variance, you know what is the typical point estimator, so then use them, right? Usually it is clear what is the best estimator, best point estimator. Theta hat exists. Suppose, and given the theta hat, we are going to add margin of error on like plus minus the point estimator, right? So you choose a point estimator, and the actual true parameter can be smaller than that or larger than that. So you allow a certain margin around theta hat, so then it gives you an interval of theta hat minus m, where m is the margin, and theta hat plus m. So this bracket means an interval, right? Starting from here to this point, to end points with bracket is the interval. So then the interval itself is an estimator, right? So it's an interval estimator. Right? We usually call this interval as the confidence interval because you are confident that the true parameter will lie within this interval, right? And the upper limit is called upper confidence limit, and lower side is called the lower confidence limit. So, like anyhow, the confidence interval is the keyword. So we call this confidence interval. And then this is correct. The interval is correct if theta, the true parameter, lies between those two limits, right? So the error probability, so we can calculate the probability that the interval is wrong, which is usually denoted as alpha. Alpha is probability that the true parameter is smaller than the lower limit, lower confidence limit. So the true parameter is even lower than the lower confidence limit, then it is wrong. You are overestimating, your interval is overestimating the parameter. On the other side, the true parameter can be greater than the upper confidence limit, which means your interval is underestimating the true parameter. So both are wrong. So the error probability, total error probability is overestimation plus underestimation probabilities. Okay. So then, other than this alpha, your interval estimator is correct, right? That is called the confidence level. Confidence level is denoted as 1 minus alpha. I don't like the notation again. Alpha is for error probability, not the correct probability. So correct probability is 1 minus alpha. The probability that your estimator is correct is denoted as 1 minus alpha, called confidence level. And literally, it is the probability that your true parameter is in between the lower confidence limit and the upper confidence limit, right? Then in that case, your interval correctly contains your parameter, which means you are correct, right? Okay, now the setup is correct. Then the next question is how to choose those two limits. That is the question. So to think about that, let's first go back to the pregnancy due date example, estimating the due date. like suppose that there are two doctors or there are two, say, different medical studies, different methods. And the first method yields due date like this, February 5th until 25th. And the second method gives you a result saying that your baby will be born between January 1st and March 31st. Okay, in these two examples, in these two methods, among these two methods, which one is more informative? It is actually pretty obvious. The first one is more informative in the sense that, so this is too wide. From any time between January and March in one day in 3 months, it's just not informative. Anyone can say that. Even you are not a doctor, you can still predict like that. So it's nothing like not any information. No true medical information is needed to make this result. So I would choose the first estimator to be more informative. But like now, let's change the question. Which has the higher confidence level? Remember, confidence level is the probability that your interval is correctly containing the true parameter. So think about which estimator is more likely to be correct, more likely to contain the actual birthday, right? The answer in here is 2, because it cannot be wrong, right? So anytime like it is just too obvious. When I say it is obvious, it's almost always true. So it cannot be wrong. Literally, it's really hard to be wrong. So estimator 2 is more likely to be correct. Then you can see some like trade-off. In my first question, which is more informative, I said the second estimator is obvious, too wide. It just says everything is possible. Simply that's what it means. I said it is bad as if it is bad, but on the other hand, it is obvious. Then that also means it's almost always true, right? Right. So this is the trade-off, right? The first estimator has a smaller, relatively smaller margin of error, so it is more informative. Like you can like restrict the way, like the date, the possible dates, but the problem is it's more likely to be wrong because you cut down too many possibilities, right? You are restricting to a short period of time. On the other hand, the second estimator, you allow 3 month long interval. It's nearly 100% correct, right? However, it means nothing. It does not contain any information. You don't need to do any like study to guess this, right? So we need to balance somewhere in between them. If it's too small, if the interval is too small, then that shows your confidence in your estimator, but it's likely to be wrong. If it is too wide, it's likely to be true, but barely any information there. So we are going to settle somewhere in between them. And in practice, what we are doing here is we choose the confidence level first, right? So like again, the smaller the margin of error is, the more informative. But at the same time, we'd like to increase the probability of correct estimation, which is trade-off. So like you have to fix one of them. We are going to fix the probability of correct estimation, the confidence level, right? We will go this way. I will choose the confidence level first, like 99%. I'd like to have a confidence level of 99%, and then minimize the margin of error. Like, so give me the most informative interval estimator among 99% confidence level, right? That is what we are going to do in practice. Usually, the typical choices are 90%, 95%, 99%. So you declare, I'm going to do estimation with a certain confidence level. Typically 95% is standard, but it means I am going to accept, I will sacrifice 5%. That's the error probability. I acknowledge that. It cannot be perfect. I allow 5%. So, and instead sacrificing the 5%, give me the most informative interval as possible, right? So then, thinking about different choices of the confidence level, which one would be would have the biggest interval? Just think about that. So the key idea is the trade-off between informativeness, which means smaller margin of error, smaller interval. On the other side, the probability of correct estimation, which is the confidence level, right? They are trade-off. So I'm asking you which yields the widest interval. That means the least informative interval, right? When the interval is wide, then because it is wide, we can achieve a higher confidence level, but it's less informative. So the answer is among these three possible confidence levels, 99% would be the widest interval because it has to contain more possibility. So the interval should be larger than the others. Okay? Okay, so now then let's choose 90 and 95% for now. And then so we would like to, so what we have is I have point estimator. Point estimator is given, calculated, and I chose my confidence level 95%. I'd like to make up an interval that contains the true probability, a true parameter with probability 95%. Then what remains to do is the margin of error. How can we find the margin of error that gives you 95% around the interval? That is our task, right? So I will do that derivation. This is the statistical expression of what I just described, right? I should have mentioned this. We will restrict our attention to the estimation for the mean, right? We are interested in the mean. This covers a lot of estimation problem in your life, so I will restrict my focus on the mean estimation. And then we know that X bar, the sample average, is the best point estimator. So the point estimator is given. Point estimator is already given to you. So we just need to calculate the margin. That means we would like to our interval will be X bar minus M and X bar plus M. And we are curious about mu, the true mean. We would like to know, we know that the probability that mu lies in between these 2 points should be 95%. That's my constraint. I sacrificed 5%, so I'd like to make the probability 95%. This is the probability that your estimator is correct. Okay. Here, let's think about those terms. So mu is unknown true parameter. So it is fixed, but it is unknown. And M is what we are going to calculate. We would like to calculate, right? So for now, it is unknown, but we would so we are going to solve it for M. And X bar is random. We learned X bar is approximately normal distribution from the central limit theorem in chapter 6. So chapter 7. So this probability is attached to X bar. So the only randomness for this probability is based on X bar. So we know X bar is the only random thing in the probability. So we are going to rearrange those terms so that the random variable goes to the middle and all the other guys are on sides, right? So I isolated the random variable X bar in here. Now you know how to do this. So I said X bar is approximately normal and you know the parameters. The X bar mean is same as single outcomes expectation and its standard deviation is single outcome standard deviation divided by square root n. So we are going to standardize X bar like so like this. This is what I just said. The mean and the standard deviations are known, like you know the formulas. So we know everything by the central limit theorem. So using the normal distribution, we are going to standardize X bar so that the standardized random variable follows a standard normal distribution. But when you standardize X bar, you have to match all the terms. So do the same transformation to keep the inequality same, right? So subtract mu. Mu is the mean, right? And sigma is the standard deviation. Mu and sigma are the standard mean and the standard deviation for single outcome. And then you can write the mean and the standard deviation of the sample average in this way. And we are going to use that for standardization and subtract mean divide by standard deviation, right? And then the mean are canceled out on each side. When you subtract mean, mu's are canceled out and you get in the end something like this. Okay? So we standardized X bar to a standard normal distribution. We did many exercises like this and it equals 95%. So in the end, the format is we have z in the middle and there is minus something and plus something. The only difference on the left and the right is the sign. So between plus minus some number, the probability must be 95%. This is what we do, right? The sum number, I denoted that as a value a. So if there is an a, number a, then between plus minus a, you need to have 95%. We need to find such an a, right? That is the idea. How can we find it, right? So when there is 95% in the middle, that means each tail contains 2.5%. So this positive a is top 2.5% value, right? We have done a similar exercise in chapter 6, so everything is interconnected. So we are looking for top 2.5% value, or equivalently, this is 97.5 percentile. We flip the inequality so that the cumulative probability is 97.5%. That is what we need to find out. So we know how to handle cumulative distribution, cumulative probability. So from Excel, let me open my Excel. So here, you know, we are going to find norm as inverse. So we are going to invert the standard normal CDF for 0.9, like 97.5%. Then you get this number. This is the number that you get when you use standard normal CDF, right? So I could find the value approximately 1.96, so 1.9599 something, approximately just I'll put it 1.96. Okay, so then that means we found plus minus 1.96 contains 95%. That's what we wanted, plus minus 1.96. And then going back one step further, 1.96 corresponds to this guy, which we obtained from standardization. So you have to equate these two, right? 1.96 is m, margin of error, divided by the standard deviation of the sample average, okay? And then you can solve for m equals something multiplied by standard deviation of the sample average. The last problem here is n sample size, n is available. You know what is the sample size, but the standard deviation is unknown. You have to estimate this again. Then I told you you can use another point estimator for the variance. The sample variance formula, using sample variance formula and take the square root, then you can just plug this in to the standard deviation, and then you get this, and so that it means you can calculate everything. 1.96 is from standard normal distribution. Standard deviation can be calculated from the data. Sample size is known, so based on that you calculated the margin and add and subtract the margin from the point estimator. That is what you do for confidence interval when you calculate the confidence interval. Okay, so this is the basic idea, and in the end, derivation may look like complicated, but in the end, it's pretty simple, right? So in the next video, we are going to generalize this derivation to general confidence level. Okay, thank you for watching, and see you later. Bye.